Imagine pointing the most powerful telescope ever built at the dawn of time, expecting to see faint baby galaxies just beginning to form. Instead, you find fully grown, massive galaxies that, according to our best understanding of the universe, simply shouldn't be there. This isn't science fiction. It's the reality scientists are grappling with thanks to the James Webb Space Telescope. What it found has been dubbed universe breakers, and they are forcing us to question everything we thought we knew about the cosmos. Just a few 100 million years after the Big Bang, a period we thought was the universe's infancy, Webb spotted 6 enormous galaxies. These galaxies are not just big, they are monstrously so, rivaling the size of our own Milky Way. According to the standard model of cosmology, the lambda-c/dm model, this is impossible. The universe was supposed to be a much quieter place back then, with matter slowly clumping together under gravity. Think of it like this. The Big Bang model predicts that early galaxies should be like small towns, gradually growing over billions of years into sprawling megacities. But Webb found the cosmic equivalent of New York City already built and bustling just moments after the beginning of time. These galaxies are not only too big, but they also appear to be too old, filled with mature red stars. Young, newly forming galaxies should be blazing with the blue light of hot young stars. The red hue of these ancient giants suggests their stars have been around for a long time, burning through their fuel and cooling down. This implies that star formation started much, much earlier, and happened far more furiously than any of our theories predicted. How could such massive structures form so quickly? It's a puzzle that has sent shockwaves through the astronomical community. The lambda-c/dm model has been the bedrock of cosmology for decades. It successfully explains so much about our universe, from the cosmic microwave background radiation to the large-scale structure of galaxy clusters. This model is built on the idea of a universe dominated by cold, dark matter and dark energy. Cold, dark matter, in particular, is the key ingredient for galaxy formation. It's cold because it moves slowly, allowing gravity to pull it together into massive, invisible halos. These halos then act as cosmic seeds, their immense gravity attracting regular matter to form the stars and galaxies we can see. The process, however, is meant to be slow and hierarchical. Small clumps of matter form first, merging over eons to create larger and larger galaxies. Webb's universe breakers fly in the face of this orderly bottom-up construction. They suggest that galaxy formation was a top-down affair, with massive structures appearing almost fully formed right at the start. This has left scientists scrambling for an explanation. The data from Webb is robust, checked and double-checked. Galaxies are real. So, if the observation is correct, the theory must be wrong, or at least incomplete. One possibility is that we've misunderstood something fundamental about the early universe. Perhaps the conditions in the cosmic dawn were far more efficient at converting gas into stars than we ever imagined. Maybe star formation wasn't a slow burn, but a massive galaxy-wide firework display that happened almost instantaneously. The superficient star formation model would help explain the brightness and apparent maturity of these galaxies. But it still strains to account for their sheer mass. How do you get that much matter, both regular and dark, to accumulate in one place so quickly? This is the heart of the problem. Another more radical idea is that we need to rethink the nature of dark matter itself. The cold in cold dark matter might be the problem. What if dark matter was warm or had other properties that allowed it to clump together much faster in the early universe? This would change the very foundation of the lambda-c/dm model. Some theories even propose that the initial seeds of these supermassive galaxies weren't dark matter halos at all. Instead, they could have been primordial black holes, formed directly from the collapse of dense regions in the infant universe. These ancient, massive black holes would have acted as gravitational anchors, rapidly pulling in surrounding gas and dust to build a galaxy around themselves at an astonishing rate. This could explain both the size of the galaxies and the presence of supermassive black holes at their centers, which is another puzzle Webb is helping to solve. The implications are profound. The standard model needs a major rewrite. It could open the door to entirely new physics. We are talking about fundamental questions. What is dark matter? What is dark energy? How did the first structures in the universe truly form? The James Webb Telescope was designed to answer these questions, But no one expected it to challenge our most cherished theories so directly and so soon. It's like finding a fossil of a rabbit in Precambrian rock. It just doesn't fit the timeline. Scientists are now racing to follow up on these initial observations. They need more data, more spectroscopic analysis to confirm the distances and masses of these enigmatic galaxies with absolute certainty. Spectroscopy is key. It involves breaking down the light from a galaxy into its constituent colors, like a prism. This spectrum reveals crucial information like the galaxy's chemical composition, the age of its stars, and most importantly, its redshift. Redshift tells us how much the universe has expanded since the light left the galaxy, which allows us to calculate its distance and age. The initial discovery was based on photometric redshifts, which are good estimates based on the galaxy's color. But spectroscopic redshifts are the gold standard, providing definitive proof. If further studies confirm these findings, cosmologists will be forced back to the drawing board. It's a moment of crisis for the field, but it's also incredibly exciting. This is how science works. A new, powerful instrument provides data that contradicts the reigning paradigm, and a scientific revolution begins. We could be on the verge of a completely new understanding of our cosmic origins. The Big Bang itself isn't in question, but the story of what happened in the first billion years after it is being rewritten before our very eyes. These universe breakers aren't just a problem, they are a clue. They are a signpost pointing toward a deeper, more complex reality than we had previously imagined. The universe, it seems, was in a hurry. It didn't wait around for billions of years to start building its grandest structures. The cosmic dawn may have been a far more violent, dynamic, and creative epoch than our models allowed, and the James Webb Telescope is our time machine, taking us back to witness it. Every new image, every new data point from Webb holds the potential for another groundbreaking discovery. We are living in a golden age of astronomy, where a single photo can change everything. What other secrets are hiding in the darkness, waiting for Webb's golden eye to find them? Don't know, and that's the most exciting part. These discoveries remind us that the universe is under no obligation to make sense to us. Our theories are just our best attempts to describe it, and they must always be ready to yield to the evidence. The James Webb Telescope isn't just taking beautiful pictures. It's testing the limits of our knowledge and pushing us toward a new frontier of understanding. If you want to stay updated on how scientists are solving this incredible mystery and other amazing discoveries from the final frontier, be sure to subscribe to Space Repo. The story of our universe is just getting started.